Hello everyone. Today we are going to continue discussing our instruction set for AVR microcontrollers. So last class we discussed some instructions and we solved some examples regarding some instruction sets. So let's start with the last example we discussed. So we discussed this example last time, and we could see that there is a typo error in the textbook. And here I modified this typo error, so you can see that here. So as you can see here, this instruction here was after adding R0, R1, which means he replaced the destination. However, he asked here to make the destination R1. So I changed this instruction here and I modified so the typo error in that example. The instruction after that is called Sts instruction, which means store direct in or direct to data space. So it's going to store in data space. The syntax of this instruction is store S K, R R means store register into location K. So it's going to store the register RR, certain register of our microprocessor, in a certain location in our space or memory, which K is address between 0000 to FFFF, any memory location in our RAM. So here is one example. The following program first loads R16 register with value of 0x55, which means 55 hexadecimal. We said that we can write hexadecimal format as 0x, then our number, or $sign followed by the number. So this is 55 hexadecimal. It would be loaded into register R16, then move this value around to input-output register of port B, C, and D. So we need to move this value to the three ports P, B, C, and D, the output ports. So simply, in order to figure out the address of these ports, we have to go to the data sheet and find out the addresses. But here it's given in this example. So 0x38 is the memory location of port B. This is a special function register for the IOs. And port C location is 35 and port D is 32. So what we can do is, firstly, we are going to upload the value of memory location 55 into R16. So it's nothing but LDI R16, sorry, not memory location. This is the value. RDI, immediate value, means this is value. So LDI R16 0x55, this means add 55 hexadecimal data in register R16, then just store in space. This is the memory location of port B, this is memory location of port C, and this is port D. So we just need to now copy the data from R16, which is our register, into these three registers, or on the output, on the ports B, C, and D. And for sure, this would be like output data now. Another instruction, which is N instruction. N means it's going to upload some data coming from outside microcontroller. So N instruction, N from input-output location. So the syntax of this instruction is N RD, A, which means load an input-output location to the general purpose register, which is D of our register here, can vary from 0 to 31, so any one of the registers, and A is our memory location of the general purpose area. You know, general purpose area in AVR size is 64 bytes, so it's here from 0 to 63. So this is for all of our memory locations. So Here, in this instruction, the N instruction tells the CPU to load 1 byte from input-output register, which is here from 0 to 63, any memory location of this one, okay, to the GPR, general purpose registers from R0 to R31. After this instruction is executed, the general purpose register will have the same value of the input-output register. Example for this, if we said here N R20, 0x16, so this means the instruction will copy the contents of memory location 16 hexadecimal, which is one of the input-output memory, okay, to the register R20. In order to figure out the address for all of the memory locations, you can find this in the datasheet. And here we have one table describing the input-output location for all of our registers. For instance, here we used 0x16. So if we look for the address 16, you will find this as bin P. So this is going to get the data from port B. Okay, nice. Take care here in the N instruction, the input-output registers are referred to by their input-output address. For example, NR20, 0x16. So we referred by the address. Okay. Instruction will copy the contents of location, memory location 016 hexadecimal of the input-output memory, which is here, we said port B, whose data memory address is 36. So as you can see here, for port B, you will find the memory address is 36. So this is now the memory address, but this is the input-output address. Okay. Into R20, which is the destination here in our instruction, as shown in this figure here, input-output address 0x16 belongs to pin B, which is the port B. Okay, so the instruction copies the content of pin B to register R20. Now, we could see that we can get the data from input port using two different ways. One is using load from space, because you can get the data from the address of the memory location or address of the input-output port, okay, and load this in certain register. And we could also use input, N, not LDS. So what's the difference? Which one we should use? Or we can use both, or one is better than the other. So let's compare between them. As we mentioned earlier, we can use LDS instruction to copy the contents of a memory location to a GPR or general purpose register. This means that we can load an input-output register into GPR using LDS, load from space. So what's the advantage of using N? So we can use N as well. What's the advantage of using N instruction for reading the contents of input-output register over using LDS? So these are the advantages here. So the IN instruction has the following advantages. First, the CPU executes N instruction faster than load from space. So in this case, we do prefer to use N instead of LDS, because it's going to be executed faster. The N instruction lasts one machine cycle, where load from space lasts 2 machine cycles. So this consumed less time in capturing the data from output ports, or from input ports. Second thing is the N is a 2-byte instruction, where LDS is 4-byte instruction. So this means if you use N, you also going to save memory locations or in your RAM. So this is going to save memory also. So it would be faster and less memory consumption, where LDS is 4-byte instruction. This means that the instruction N occupies less code memory. Third thing is when we use an instruction, we can use names of input-output registers instead of their addresses. So this is easier. You can just name your port. Okay. Last thing is the end instruction is available in all the AVRs, whereas LDS is not implemented in some of AVRs. What the advantage of the last thing? The advantage is if you are going to switch between one microcontroller to another one, so the code would be more general if you used N instead of others. So this could be helpful if you would like to replace your microcontroller by another chip from the same family AVR. Let's see together one example here. State the contents of RAM location 212, 200 to 216. So this part of the memory location, 4 registers, 12, 13, 14, 15, 16. So 5 registers from 12 to 216 after the following program executed. So we have a certain program. In order to manage this, you need to write the different memory location and check the values after each instruction. So you have here LDI R16 with 0x99, which means immediately load data of 99 hexadecimal to register R16. Then STS store in space R16 to 212. So this is going to copy the data in R16 into the memory location 212. Then LDI R16 with value 85, and then move it to 213. So 213 now would have the value of 85, and so on. Loading R16 again by another value, which is 3F, and moving R16 to 214 memory location. Then loading R16 with another value, which is hexadecimal 63, and move it in 215. Then load immediately immediate value 2 or 12 into R16, and then store in space at memory location 216 the value of 12. So if you would like now to see the different memory location, you can just make like that, a table like that. We have memory locations from 212, 213, 214, 215, 216. After the first two lines here, we can find the value in 212 is 99. So this is our value here. Then after the second instruction, the 213 would have 85. So this is 85. Then 14, 15, 16 would have the value of 3F, 63, and 12. So this would be the result of this example. So here in this example, we knew that you can transfer data from a register to a certain memory location in your memory. Now let's see this example. We have some registers. So state the contents of registers R20 and R21 and the data memory location 120 after the following program. So we have 3 memory locations we need to identify what the value inside R20, R21 registers, and memory location 120 after executing the following program. Firstly, LDI R25. So this means upload this value and take care there is no 0x or $sign. So this means this value is decimal value 5 into R20. So the register R20 would have now 5 inside. LDI R21 2. So this means R21 after executing this instruction would be or having data T2 decimal. Add R20 R21. Add all of time will add the inside values of this register, and the destination or the result would be in the first part here, which is R20. So this is going to add 2 and 5 together and both the result in R20. So R20 firstly was 5, but after executing this instruction, it would be 7 decimal. Then again, add R20, R21. So R20, after executing the previous instruction, it was 7. So adding 2 again, which is the value in R21 to 7, so it would be 9 after executing this instruction. And finally, STS or stored space R20, which is the result of the two summation values, which was 9 here. Okay, move this value or copy this value and store it in a memory location 0x120, which is 100x hexadecimal 120 in your memory location. So the results here, as you can see, these are all of the instructions. For sure, you can make a different table to make it much easier for you. But we said, firstly, after executing the first one here, so R20 would be 5. Then the line after R20 would be 5 as it is. 21 would be 2. And still memory location, we don't know what the value inside. We neglect that because it's not initiated. And then after executing the instruction, add R21 and R20. So this means R20 here would be the result, which is 7. R21 is still 2. 120 is still unknown. Then adding more 2 to R20, it would be 9. And still 120 is unknown. 21 is still 2. And finally, copy the results to memory location 120. So 120 finally here would be 9. So these are the values inside these registers after executing such code. Typically, like we can input data from outside microcontroller. We can also output data to the devices outside microcontroller. So we have out instruction, okay? So out to a certain input-output location. So the syntax of this instruction is out A, R, R. This means store register to input-output location. So you are going to copy the data from certain register to the memory location of the input-output ports. And here you have little r, which can be from 0 to 31. So this can be used with any registers from R0 to R31 from the processor registers. And for the destination A, which is the memory location of your input-output port, it would be vary from 0 to 63 according to the input port you need to output the data. So after the instruction, or firstly, the out instruction tells the CPU to store the general purpose register to the output register. So it's going to store the data from general purpose register to input-output register. Also, after the instruction is executed, the input-output register will have the same value. It's not going to be changed in the registers. It will be the same, but it just will be copied to the output port. For example, out port D, R10. This means an instruction will copy the contents of R10 into port D, which is located at 12 of the input-output memory. So let's see more details for this instruction. Notes: the output instruction, the input-output registers are referred to by their input-output address, like input instruction. So we refer to the port by address, okay? We must remember that we cannot copy an immediate value to the input-output register, nor to SRAM location. As we discussed this earlier, we cannot copy a certain value, but we have to use registers in order to store the data firstly in registers, like using LDI, and then copy the data from registers to the input-output or memory location. Another example here, guys. Write a program to get data from pin B and send it to the input-output register of port T continuously. Continuously means anytime during the program. So this means, guys, you need to have like monitoring for the registers in order to copy the data all of time. How can we do that? Let's see together. We will use one of the branching instructions, and later on in other classes we will discuss in more details what the meaning of branching, loops, and everything. So here we will give a name for the line. So here we call this name again. You can add whatever the name for this line, but once you add a certain string here and add 2 dots like that, or colon like that, so this means this is the name or the label of this memory location. Okay, so again, and then I will write the syntax, which is n R16, port or pin B. Take care that in N we use pin, not port, but in out we use port, not bin. What's the difference? We said previously, in order to assign the ports, the I/O ports, to be input or output, we have different latches or different inside transistors. So in order to activate the latches for the output, you have to enable some buffers, and in order to make it for input, you have to enable other or different buffers. Okay, for that we have different syntax or names for the same port if you are going to use it as input or output. So for N we use pin, and for out we use port. But physically, either pin B or port B would be the same port and the same pins in the microcontroller. However, if you are going to use it as input, you should use pin. And if you are going to use it as out, you should use port. So here, NR16 pin B means bring the data from port B into R16. So this is going to copy the data from port B into register R16. Then out port C R16, which means it will copy the data from R16 to port C. So this is what happened here. Again, we could not make copy from the data of port B to port C immediately. You have to use registers in between. You cannot copy the data immediately between ports. Okay, so this is the way here. So here we made out port C R16, which means copy the data in register R16 into port C. So this means send the data out to port C. In order to repeat this operation, we just going to jump. So jump here means go to the address which has name again or label name again. So it would now move to N again, and it will continue moving the data from port B to port C. Okay. Later on, we will discuss all of jump and loops operating instructions. Another instruction, guys, is called move. Move instruction is used to copy data among the GPR registers. So in order to copy any data between registers, you can use move instruction. So this is going to move the data from one register to another register. So for instance, move RD, RR, this means RD would have the same value of RR. And RD and RR can be any of the GBRs, which is from 0 to 31. For example, move R10, R20. This means the data in R20 would be copied into R10. So after executing this instruction, R10 would be equal to R20. So R10 equals R20 after executing this instruction. For instance, if R20 contains 60, value of 60, After executing this instruction, R10 would have 60 as well. And R20 would be the same because there is nothing happened to the register, which is the source of the data. Okay, so the source of the data would be copied onto the destination, but the source and destination would have the same value after executing this instruction. Increment is typical like the other programming language. So increment certain register is going to increment the value inside this register. We can use increment instruction with the registers RD, where D can be any register from 0 to 31, the general purpose registers. So the inc instruction increments the contents of RD by 1. For example, inc R2 means R2 equals R2 the first value plus 1, which means it's incrementing R2 register. The following program increments the contents of data memory location 0x430 by 1. Let's see together how it can make this. For instance, LDS R20 0x430. So this means the content of the memory location 430 would be copied into R20. Then increment R20 means the data inside 430, which has been copied to R20, would be incremented by 1. Then STS 430 R20, so this is going to store R20 to the location 430 again. So take care that the value of 430 would be the same. This is just memory location. However, the value which has been incremented is the data inside the memory location. Okay. Let's see if there is numerical example here. So no numerical example. So let me go back again to give just one example here with numbers. So for instance, if you have if you have, for instance, the memory location 430, assume that this memory location has certain data of, for instance, 1, 2 hexadecimal. So this means when you execute the first instruction, R20 would have the same data which is exist in the memory location 430. So after executing this instruction, we can say the data inside R20 would be 12 hexadecimal. Then increment R20 would increment the value which is 12. So after executing this instruction, so R20 now would be 12 plus 1 hexadecimal, which is 13 hexadecimal. Then storing the data from R20 into 430 memory location again. So after executing this instruction, the memory location 430 would have a data of 13 hexadecimal. Okay, so this would be the numerical, and this is a numerical example to just figure out how this instruction is working. Okay. Sub instruction. This is another instruction. We use it in AVR processor. So the sub instruction is nothing but subtraction. So sub RD, comma R means RD equals RD minus RR, which means you have two values inside these two memory locations or general purpose registers, and if you subtract the value, so the source registers are RD and RR, and the result of the subtraction would be stored in RD. So for that, we can say RD register, after executing this instruction, would have RD initial value minus RR. For instance, let's see an example here. The sub instruction tells the CPU to subtract the value of RR from RD and put the result back into RD register. To subtract 25 hexadecimal from 34, one can do the following. So let's load immediate R20 by 43. So sorry, 34. So here R20 would be hexadecimal 34, and then load R21 by 25 hexadecimal. So R21, not 20. So here we have typo also. So R21 would be 25 hexadecimal. Then sub R20, R21 means R20 would have R20 minus R21, which would be now 34 minus 25. Okay, so this would be the result. So the result here, finally, the value would be 34 minus 25. But take care for sure, this is hexadecimal. Okay, so this is how to execute the sub instruction. Another example here, the following program subtracts 5 from the content of memory location 300 hexadecimal and stores the result in a location in the memory, which is 320. For instance, how we can do that? Firstly, let's see, LDS means loads a certain space, R0 0x300. So this is going to copy the content from memory location 300 into R0. Okay, so the content of 300 hexadecimal would be moved to R0 register. And then LDI R16, this is another register with 5 hexadecimal. Take care, LDI cannot use registers from R0 to R15. You have to start from R16 up to R31. So this instruction is right here. So R16 equals 5 hexadecimal. Now you can subtract. So you can say now sub R0, R16. So R16 has internally 5 hexadecimal. We don't know the value inside the 300, but now the sub R0 minus R13 would subtract the value inside R0 minus the 5 hexadecimal, and the result would be stored in R0. Then moving this R0 again from R0 to 320 in order to return the result into 320. So this would be the program to execute this subtraction process. The following program also decrements the content of R10 by 1. So here, in order to make decrement, so decrement is typically like subtract minus 1. So decrements is equal to the value minus 1. It's like increment adding value by 1. So LDI R16 by 0x1, which means that value in register R16 would be 1 hexadecimal. Then subtract R10 R16. So this means it will decrement the value by 1 because we stored 1 in the memory location R16. So it's equivalent to decrement by 1. Now, what are the different instructions in arithmetic and logic units that are using GPR registers? So all of instructions are like that: add, This is to add two numbers. Add carry. What's the meaning of add carry? Now, guys, if you have a data of 8 bits, and you know all of registers in AVR microcontroller in our family now, which is 328, it's 8-bit processor, which means all registers and all memory location data are 8 bits or 1 byte. So what will happen if the summation of two numbers is greater than 8 bits? In this case, the result would be for sure wrong, because you don't have enough memory space to add the data, which is greater than 8 bits, in a size of 8 bits. So what happened is the memory location of the 8 bits will be filled with data, and the remainder number will not have any place to be stored. In this case, one of the registers we have in our processor, we are going to discuss this register in the next class, which is called the status register or flag register. It will have one bit called carry. So if you make add with carry, this means if you have a data greater than 8 bits, the data will be added, and the result, or let's say the incorrect result, because the data is higher than 8 bit, so only 8 bit of the data would be stored in RD, and the carry flag would be active high. So this means add with carry. How can we detect that? Just check the carry flag in the flag register. So if carry flag is active high, this means your instruction or the addition instruction here is invalid, which means you cannot use the data now to continue your program. How can we solve that? We have many techniques. We can, for instance, divide the 16-bit data into 2 registers and adding in 2 registers instead of 1 register. So later we can see some examples on that. However, for now, what's the advantage of add with carry? Add with carry is going to let you know if carry flag is active high, so your result is incorrect. So this is just flag. It's not going to solve the issue, but it will just let you know that you have an issue in your program. Okay. So this is called add with carry. You can use also with the general purpose registers. You can use AND, which is logic. So AND RDRR. So this means AND RD with RR. And the result of the AND gate finally would be stored in the destination, which is RD. Okay. EOR or exclusive OR for the 2 registers, and the result also would be stored in RD. OR register, so it's going to make OR logic for RD and RR, and the result would be stored in RD. Sub T, so this means subtract with carry, RD and RR. Okay, so this is with carry, which means if you have carry as well, so this means your subtraction is incorrect. Sub without C, so just sub, this means subtracting RD, RR. So it's going to subtract RD minus RR, and the result would be stored in RD. Okay, and this is without carry for sure. So these are the most instructions that we can use with general purpose registers. Also, you can use some instructions with general purpose registers like CLR or clear. So clear means clear register RD, which means clean the register from any data. So it would make all of register zeros. Okay, so clear RD, after making this instruction, assume clear, for instance, R1. So after clear R1, the value inside R1 would be 0, 0. Increment, so this is going to increment the value as we discussed. Decrement, it will reduce the value by 1. Com, means complement. Okay, so it's going to make complement for the values inside this register. NEG means negative or tooth complement of a certain value inside the register. ROL means rotate left for the register RD through carry. So this would add carry flag and rotate the contents inside the register to left side. Rotate right for RD means rotate right RD through a carry flag. LCL means logical shift left. So it's going to logical shift data to left for the register RD. LCR means logical shift right for register RD. ASR means arithmetic shift right RD. Swap means change or exchange the data inside the two nibbles of your byte of your register, which means, for instance, if you have data in register like 4A, so after making swap, so the data would be A4. So this is the meaning of swap for the data of your register. So we have here some rotate left, some arithmetic left, right, and so on. Let me just elaborate more, guys, in this point in order to understand what the meaning of this left or shift or logical shift or arithmetic shift. So for instance, let's see together the left logical shift. So this is logical shift, which means shifting the data in your register to left. So after shifting, what would be added in the first bit here? The data should be added here is 0. So for the logical shift, left shift, you will add 0 in the first bit, and the data would be shifted to the left like that. So as you can see, this one comes in the second bit, and so on, and last 0 here comes on the most significant bit. For the right logic, so you will shift register to right. So here you have one data, it will be deleted, it's not going to be shifted. The one would be shifted here, and a 0 will be inserted in the last most significant bit. So this is the left logical or right logical instruction. What the difference between left logic and left arithmetic? Let's see together. If you have a look to the instruction or the construction of the code here to that construction, you would find it's similar. So we can say left arithmetic is typical to left logic. However, right arithmetic is different because right is going to add 1 instead of 0. So this means, as you can see here, for the right logic, we added 0 to the right. However, for the right arithmetic, we added 1. Okay, so this is the difference between the two instructions. Okay, later on in our applications, we will see how we can use these instructions in our codes. Com or complement, this is another instruction. We use it a lot in our programs. So the com RD, or the instruction com for register RD, means complement or inverts the contents of register RD into the register, okay, which is given here, RD, okay. So in the following program, for instance, we put 55 in R16, and then we send into the special function register location at port B. Then the content of R16 is complemented, which becomes AA. So 55, when be complemented, it can be AA. We can see that how it can be complemented together. For instance, the 55 means 1010, and another 1010 for the other 5. So this is now 55. If you complement means first one instead of 1 would be 0, then 1, then 0, then 1. So if you add 1, 0, 1, 0, it would be A, okay, which 1, 0, 1, 0 means here you have 2 and here you have 8. So 2 plus 8 is 10, which is represented as letter A in hexadecimal. So this would be the value of 55 complement. So let's see together the instruction here to implement this code. So firstly, LDI R16 with 55 hexadecimal. So R16 equals 55. So this would store data 55 in R16. Then out port B R16. So the 55 would be stored on the memory location for port B. So this means copy R16 to port B special function register, which is already stored in a certain memory location. Okay, nice. Then which complement R16. So R16 now the value inside would be AA instead of 55, and then output B R16. So the data in R16, which is AA now, will be stored in the port B output. So the port output would be complemented. So for instance, guys, if we are connecting some LEDs to that port and we implement such code and repeating this code with a certain delay, for instance, between each instruction, you can see these LEDs are blinking on that port. Okay. Let's see this example here. Write a simple program to toggle the input-output register of port B continuously forever. Continuously forever again. So this means you need to repeat your code, which means you have to use branching codes like jump, for instance. So let's see together. So let's load the values again in order to have the port bins toggles. So you need to have the bin active low, then active high, and so on to be continued like that. And in order to have one bit is on and the one after that is off, so the right value would be 55 and AA, like what we could see in the previous example. So let's store in R20, store value of 55 hexadecimal, then output this to a certain port. So output B by R20. So this is going to move 55 hexadecimal to port B. After that, complement the content of R20 and out this to port B. So the data on port B now would be AA instead of 55. Then jump to L1. L1, just you can start from here, which is going to complement the R20, and after that, output this data to the output port. So it will stay forever looping in these two conditions or two instructions in order to output the data to your port. However, take care, guys. This instruction is going to be executed in very few microseconds according to our processor, which means if you apply this software and try to see that on your port, you will not figure it out because the speed of a change will be very, very high. You cannot figure out this speed. Okay, in order to figure out this speed, you need to reduce the frequency of on-off. For instance, guys, you know that the electricity here in the United States is 60 hertz, which means any AC supply connected to any light, it will cross the 0 volt 2 times per 1 cycle, which means 120 times per second. Can you figure out the lamp is turning off for 120 times per 1 second? For sure, we cannot figure out that, okay? Because our eyes cannot recognize this fast change in turning on and off. In order to figure out that, you need to make a delay between each turning on and off. So in order to do this blinking for our LEDs, you need to add delay after, for instance, after this instruction, before jumping here, make delay for certain time, let's say, for instance, several hundreds of milliseconds, okay, in order to figure out that, in order to see the change of the LED lights, okay. So this is our contents for today. So we covered most of instructions which are related to the to the memory. Okay, so in this class, guys, we could, in this class and the previous slide, in this slide, we could compare and contrast microprocessor and microcontrollers. We could discuss the criteria for selecting microcontrollers, figure out how to select microcontroller, figure out the pin configuration of our processor, 80 mega 328 processor, discuss the general purpose register orientation, and coding using assembly language for AVR instructions. So these are the objectives of these slides. Next class, we will consider some assembly language instructions related to something else, related to some other memory, okay, and discussing the branching and other things. From the next class, guys, we are going to use our program, which is Microchip or Atmel Studio. Okay, so hopefully next class, all of you, I hope all of you could install this program, because from the next class, we are going to solve some codes together on that program. Thank you so much, and see you next class.